about the matrix bootstrap and some of its applications. Okay, this is my first list. Like this?
No, take it up, please. You have to rotate. It's like this.
Okay, great. Yeah, so the course is going to be about the matrix bootstrap, and I've listed some references here. We'll discuss some more references as time goes on. So I would start by giving some motivation. So my personal motivation, which is only one possible angle to approach the subject, is solving black holes. Okay, so I would like to solve black holes in a theory of quantum gravity. And by solving black holes, I mean solving the dual quantum system that describes the black holes. Okay, so computing simple correlation functions, for example, in the dual quantum system. That's the goal. Okay, so there are some immediate problems with doing this, even numerically, right? So first problem is we need large n. Why do we need large n? It's just because this famous formula, right? The G Newton is in the denominator. So if we have a semi-classical black hole, this is a very big entropy. Very big entropy means large n, right? So this is one consequence of the horizon of the black hole. A second difficulty is we need strong coupling. And again, this is a consequence of the horizon, right? So we now know that semi-classical black holes, the ones described by Einstein gravity, are maximally chaotic. So the dual quantum system saturates the chaos bound, right? So whatever quantum system that we're going to try to solve, it's not going to be, in general, a good idea to use perturbation theory. Okay, third challenge. These challenges are a little bit less minor, I think, are a bit more minor compared to the first two challenges. But nevertheless, one issue is metastability. Okay, so there are certain problems that are well defined at infinite n that are, strictly speaking, not so well defined at finite n. And black holes are sometimes included in this category because black holes can Hawking evaporate. So in particular, in the BFSS context, which we'll discuss probably in the future lectures, these black holes can evaporate. And this evaporation is an effect that goes away at infinite n. But at finite n, it exists. And so to really isolate the black hole is going to be tricky at any finite n. Okay. And the fourth is the sign problem. Okay. So the sign problem means if we're going to try to simulate the quantum system using a classical simulation, like a Monte Carlo simulation, it's going to be very difficult, right? So in particular, there's two reasons. One is if we're interested in Lorentzian physics, which of course many of the puzzles involving black holes involve Lorentzian time in some way, in some crucial way. And second issue is even if we're interested in some Euclidean partition function or thermodynamics, the black holes that we know how to describe in some dual quantum system in string theory, they're usually supersymmetric quantum systems, right? So they have fermions, and the fermions means so fermions means that in general we have to worry about the sign of the Pfaffian, right? So these four problems will make it difficult to try to solve any strongly coupled large n quantum system, right? The ones that are relevant, let's say, for black hole physics. Of course, if you don't care about black hole physics, there are many problems which have some of these challenges. And I think it's a nice question, what other applications of ideas that are sort of in this neighborhood that sort of are different than the ones I'm going to emphasize in this sort of mini course. Okay, so just a final comment. So I sort of have Monte Carlo in mind when I say that these problems are challenging. Of course, you can still try Monte Carlo, and there's many important Monte Carlo results, which we'll probably mention a little bit more next time. But they, of course, how they work is they start at finite n and they try to do some extrapolation. They, for example, try to regulate the problem in some way to remove this metastability. And they try to go to strong coupling by making a very big thermal circle. So we'll discuss that a little bit more in detail. So I'm not saying that it's impossible to do the classical simulation, but I'm saying it's extremely non-trivial. And we would like a method which sort of deals with these problems in a more natural way. Okay, so that's the motivation. Please interrupt me at any point with questions.
Isn't there another problem, which is that since it's a chaotic system, if you're in the black holes or the high energy states of the spectrum, you're not supposed to be able to compute those numerically.
I wouldn't say so. So, for example, in the BFSS context, you can go to very small, it's very easy to go to high energies because you can make a very tiny thermal circle.
But if you're trying to get the states which are black holes, which are higher up in the spectrum, you're not going to be able to compute their
Yeah, certainly like an,
accurately if it's a chaotic system.
okay, well, yeah, certainly like if you're doing the bootstrap, let's say conventional CFT bootstrap in n equals 4 super Young mills, it's going to be very difficult to access these high energy states, that's true. But let's say from Monte Carlo simulation of, let's say, BFSS, they can actually go to high energies very easily. Of course, they can't give you the detailed energy spectrum, but they can tell you the thermodynamics, for example. They can test this formula to some extent.
You just want to see statistical properties.
Yeah, I think the zeroth order question that we would like to answer is just these simple correlators, like thermodynamics, 2-point function, 1-point function, this kind of stuff. Okay, so I'm going to keep this up here, and now let's just jump into the matrix bootstrap. So I'm going to explain now the matrix bootstrap in the simplest possible context, which has nothing to do with black holes, okay? So this was just motivation, but even in the simplest possible context, we will see how the matrix bootstrap can possibly address these kinds of challenges. Okay, so what is the simplest possible context? The one that I know of is the one matrix model, okay? One or perhaps 1 plus matrix model. So this is just a probability distribution, P of M, which has the form, let's say, e to the minus s z, where s is some polynomial in the matrices, right? So it's a single trace, let's say trace m squared plus v to the m, okay? Some polynomial in the matrices, and we can use some normalization like this. Okay, so the question is, the question that we want to answer is twofold. One, we would like to know, we would like to know all moments of this probability distribution, right? So we would like to compute, let's say, trace m to the k with respect to this distribution. And sort of a zeroth order question that's even before this one is we would like to know when this probability measure makes sense, okay? So we would like to compute the moments when it exists, and if it doesn't exist, we would like a warning that it doesn't exist. Okay, so what do I mean by this? Well, obviously, if this potential is positive, okay, then this problem exists, right? If this potential is bounded from below, this problem is going to exist. But let's say if the potential looks like this, right? It'll be less obvious whether or not the problem exists. So at finite n, this certainly won't exist. But at infinite n, because of metastability, it's possible that these moments actually exist at infinite n, even though they don't exist at finite n. So we would like a simple way to know whether or not this problem makes sense. Okay, is the statement of the problem clear? Okay. All right, so how are we going to do this? Well, the method is extremely elementary. It's almost embarrassingly elementary, okay? So there's 2 ingredients in any bootstrap. The first ingredient is some kind of positivity. And the second ingredient is some kind of consistency. In this case, we're going to use the equations of motion. So we're going to think of these as some sort of consistency equations between different correlation functions. So in this context, some people sometimes call these the loop equations. They're really just the Schwinger-Dyson equations applied to the one matrix integral, okay? So M here is a Hermitian. We're assuming also M is a Hermitian n by n matrix. And we're going to work in the 't Hooft limit, so the strict n goes to infinity limit. And let's review first the second aspect, okay? So what are the Schwinger-Dyson equations in this context? Well, there's a very simple way to derive them diagrammatically, okay? So we consider some blob that represents trace m to the k, right? So it has k external lines. For this purposes of this talk, we will not need to use the double line notation, okay? Okay, so we consider external blob, and the idea is that we follow one of the external legs into the blob. Okay, so we just choose one of the legs, we follow it into the blob. Okay, so there are 2 possible things that can happen, okay? The first possibility is when we follow this line into the blob, there's no vertex. It encounters no vertex, okay? So if it encounters no vertex, it just becomes another external line, of course. And it splits the blob into 2 pieces. there can be no line crossing from here to here because of large n factorization, right? Because of the planar limit. So here we're summing only planar diagrams, and a line that goes from this blob to this blob would cross this guy and it would be non-planar. Okay. There's one other possibility. So this was the case where the external line encountered no vertex. The other possibility is that it encounters a vertex. So if it encounters a vertex, what happens is it simply increases the number of external legs in this blob. Right? So in terms of an equation, right, here we have a sum of double traces. Right? Trace m to the l, trace m to the k minus l minus 2. Sum from l equals 0 to k minus 2. Right? There's a minus 2 because we lost 2 external lines using this propagator. Right? The other possibility is that it encounters a vertex. So if there's some coupling g, so I'm imagining, let's say, v equals 1/2 m squared plus g m cubed, let's say. If it encounters a vertex, then it just increases the degree of the correlator. Right? Previously there was just 1, now it becomes 2. And this is the Schwinger-Dyson equation. Okay? Okay, so what's the point of this? Well, the idea that we're going to, the perspective that we're going to take on this equation is that we think of this as a recursion relation between higher correlators and lower correlators. Okay? So both of these two terms, they only involve matrices of degrees, they only involve so-called words of length up to k, right? So we think of this as a trace of some alphabet, right? And the alphabet in this case is just one particular matrix. If there were more matrices, there would be, there'd be A's and B's, for example. And they're words of up to length k. The only term in here which has a higher degree is this term here, right? So the idea is if we knew some low correlator, we could plug it into this equation and generate a new higher correlator, right? Then we would learn that value of that correlator, we'd plug it in, and we would generate even more higher powers of trace m to the k, right? Okay, so the idea is, so the idea of the bootstrap, let me now erase this. So the first aspect of the bootstrap for the matrices is that we simply do a guess and check sort of algorithm, right? So the idea is that we guess some low correlator. Let's say trace m, for example. We plug it into the loop equations, and that generates many, many other correlators, right? It'll generate trace m squared, trace m cubed, trace m to the 4th, et cetera, right? Based on our initial guess, right? And now we would like to check. So the first step is to guess. The second step is to check. So what do we check? Well, we have to check some kind of positivity, okay? So what is the kind of naive positivity that you could check? The simplest thing is you could just check, for example, that even moments are positive. Right? So if I calculate trace m to the 2k based on this procedure, and I find that, let's say, trace of m to the 100 is minus 0.3 based on my initial guess, then obviously I can rule out my initial guess, right? M here is a Hermitian matrix, so m squared will be a positive matrix. Okay? So this is the most naive thing. There's something slightly more sophisticated. So the idea is we can create this inner product matrix, or a Hankel matrix, MKL, which is just defined to be the expectation value of trace m to the k plus l. Okay? And the idea is that this matrix has to be positive semi-definite. So why is that? Well, we can consider an arbitrary polynomial, p of m. Okay? This is an arbitrary polynomial in the matrices. Right? Then we know that p of m times p bar of m, expectation value, is positive, right, for any possible p. Right? This is a very minor generalization of this idea. Right? But p bar m, pm, if we just expand it out, right, this is equal to trace m to the k plus l pk bar pl, right, summed over k and l. I've just expanded out the definition of this thing, right? And since this is true for all possible p's, this implies that this quantity, which we called mkl, is positive semi-definite. Okay? So extremely elementary argument. Yes? Yeah, I'll just repeat the question. Does it hold in multi-matrix context? So the idea is, in a multi-matrix context, maybe let me answer that in just 1 minute. The answer is that yes, there's a generalization. Okay, but in this simplest context, we just argued that MKL is positive semi-definite. So it's so slightly more sophisticated strategy is we assemble this matrix M, right? So based on our initial guess, we populate this matrix of inner products. So this is just, right, trace 1, which is 1, trace M squared, etc., right? This is a positive this matrix is a symmetric matrix, and we calculate its eigenvalues, let's say, based on our initial guess, and we check whether all the eigenvalues are positive. If we find a negative eigenvalue, we rule out the guess. Okay? It's an extremely simple algorithm. Yeah, so let me just comment while we're on the subject. First, I've used large N, right, in writing the factorization, so that's how we use large N. Strong coupling, well, this argument, so far you see the ingredients, they can work for any value of the coupling. So strong coupling in principle is not a problem. And now we will address 3. Okay. What to erase? Maybe erase this. Okay, so we can make some plots, right? So for example, we can plot something like a trace of M, or really any correlator. It could be trace M squared, for example, as a function of the coupling G. Okay, this could be, again, the G that I wrote there. It could be G M to the 4th. And we get some plots that look like this, right? So if we calculate a finite matrix M, so we cut it off at, let's say, some power, which we call the level. Let's say level 4. Okay, that just means a 4x4 matrix M. We calculate its eigenvalues, impose that it's positive. We get some allowed region. Okay, and the allowed region gets smaller, of course, as we impose more and more constraints. Right? As we impose more and more constraints, this region becomes extremely tiny, and it eventually approaches the exact solution. Right? We can, of course, solve this one matrix model using conventional techniques, right? By going to the eigenvalue basis, etc. So eventually it approaches the exact solution, and if you do it on a computer in Mathematica in about 1 or 2 minutes, you can code up this exercise, and just by considering, let's say, 10 by 10 matrices, you can already get very, very close to the exact solution. Okay, so if you want multi-digit precision, it's very easy in this one matrix model context. Okay, but it's not so impressive that we solved the model that's already analytically solvable. We just solved it using some new method. Of course, we would like to eventually solve models that can't be solved, but this is the simplest context, and we can make sure that this method actually works in this context. So here, so this plot actually corresponds to a potential where G means G trace M to the 4. So it's a quartic potential, let's say. Okay, so this is a positive potential, right? So we can make G arbitrarily large. But we're working in the 't Hooft limit. So G is actually the 't Hooft coupling in this context. And as you're probably aware, the 't Hooft expansion usually has a finite radius of convergence, right? So it makes sense to discuss the values of G that are negative, right? And this corresponds to a potential that is unstable, right? That would be unstable at finite n in particular. So the exact solution just can be analytically continued to negative G up to some point, okay? This point is the radius of convergence of the 't Hooft expansion, right? And you can simply ask what happens to this plot as we continue to negative values of G, right? So let me just clean up this plot a little bit. So let's just plot values of G which are now negative, right? So here's the value of the radius of convergence. In some conventions, it's -1/12. It doesn't really matter. What we see is the following. So at some finite level, it looks a bit like this. And as we increase the level, we quickly converge to, again, the exact solution. And in particular, there's a peninsula here, right? So the peninsula means that if G is slightly below this critical value, it's allowed for some amount of time, right? So for some number of levels. As we increase the levels, the tip of the peninsula quickly shrinks to the exact radius of convergence, right? So this means that the bootstrap finds the correct values of G for which the model makes sense. Okay, for values of G less than this critical value, the picture you should have in mind is, well, we have some eigenvalue density sitting here. And for G more negative than the critical value, these eigenvalues can spill over, right? At finite n, they could also tunnel over, but that tunneling is an e to the minus n effect. So at infinite n, we can ignore that phenomena. Okay, so this allows us, if we want, to estimate, for example, the exact value of G, which is the domain of analyticity of the 't Hooft expansion. Okay, and the reason why I'm emphasizing this is simply to show you that, at least in this very simple context, metastability is not a problem for this single matrix integral. Okay, yeah. I can also repeat. Yeah.
Do you have some idea of how to access the double scaling limit?
I think, yeah, in principle, one needs to discuss 1 over n corrections. And, well, with Zetron, we discussed a little bit the first 1 over n correction that can be bootstrapped. How to go really beyond that and, yeah, really work at fixed double scaling parameter, I'm not sure how to do. Yeah, of course. So, yeah, of course, at G equals G critical, that's where we make contact with the minimal string, right? So, yeah, similar question is in, let's say, the BFSS context, how do we go beyond the 't Hooft limit, which would be extremely interesting. Okay, so this is the story for the one matrix model. As I said, it's a model that can already be solved. So we're just calibrating our method by solving some model and making sure that we know what we're talking about. Okay, now we can go to a more interesting context, which is, let's say, the 2-matrix model or multi-matrix model. Okay, and we will immediately encounter some, well, some technical differences, right? So first of all, let's think about the loop equations. Well, now we will have different colors, right? So we could have some black matrices and some red matrices, right? So I don't know, some of these could be a different color, and that would represent something like, you know, trace a squared, b, a, whatever. You know, some words made out of the 2 matrices, A and B, right? And we will have many different blobs, right? So in particular, the number of words will grow exponentially with the length of the word, right, for a multi-matrix model. Whereas there's basically one correlator for each length of the word for a 1-matrix model, okay? So that's one difference, but we also have many more Schwinger-Dyson equations. So we have many more variables, we have many more Schwinger-Dyson equations, and the reason is previously we could follow any line into this blob, and we got the same equation, right? But here, if there's different colors, well, we can follow a different line in, and depending on whether it's black or red and its exact position, we'll generically get a different equation, okay? So we also have exponentially more equations of motion. Now, we also have exponentially more positivity. So let's think about that briefly. The idea is very simple. So the idea is, instead of considering these polynomials in just one matrix, we just consider a general multivariate polynomial, right? So, okay, we have P of AB. It will be some, in general, some complicated expression involving A's and B's, right? We could have A, also AB, BA, all possible orderings, right? These will all have some different coefficients. So we could call this P0, P1, P2, etc. And in general, we will consider some arbitrary superposition of words, right? And then we consider the corresponding matrix M, which now we don't have a simple expression like this, but still, it's some giant matrix. In principle, it's exponentially big matrix, and we can calculate it for any finite cutoff, right? So for any finite cutoff, we calculate this matrix, and again, we check positivity. Okay, so that's in principle the algorithm. Now, there are several challenges. One difference is, whereas before, if you knew the value of a small number of correlators, maybe 1 or 2 correlators, like trace of m and trace of m squared, you could produce infinitely many more. You could produce all the other correlators based on just 1 or 2 of these things. So in this simple algorithm which we discussed, where you just scan, works pretty well, because you only need to scan over 1 or 2 values of unknowns, right? In the multi-matrix case, this is no longer true. So it's not true that there's some finite number of correlators that if you knew, you could predict the rest of the correlators, even at infinite n. Okay? So this means that in principle, you have to scan over many, many variables, which is going to be difficult. Okay? So yeah. One more minor comment. So this equation is not a linear equation, right? We used large n factorization to get a series of quadratic equations, right? And in the multi-matrix context, we will have some quadratic equations in many, many variables, right? So this will not be a standard semi-definite programming problem, right? A standard semi-definite programming problem, you have some positive matrix, but of course, the constraints relating the different matrix elements are all linear. Here, there's some quadratic relations that relate the different ones. But this can be solved by a method proposed by Kazakov and Zhang. Okay, so the idea is that you can do nonlinear relaxation of these quadratic equations and therefore do a semi-definite programming. So let me explain that very briefly. So let's do a baby version first. So we could have, in this, excuse me, in this equation, we could have something like, for example, trace m squared appearing. And the first idea is we define a new variable q, which is equal to this combination. Okay, so far we've done nothing, right? We now substitute q into that equation, and now we have a linear equation in q and the other unknowns. Of course, we just renamed, so far we've done nothing, we've just renamed some quadratic combination q, right? But now the idea is we remove this equality. We remove it and we replace it by a different equality. And I'm going to write the equality in a stupid way, or in a smart way, actually. So let's call this unknown variable x, right? This was one of the variables that, you know, if we knew the value of x, we'd be able to generate many of the other correlators. And we replace this equation with this inequality. Okay, so this matrix being positive semi-definite, what does it say? It says that 1 is positive. That's good. And it also says that the determinant of this matrix, which is q minus x squared, is positive. Right? So what have we done? We've just replaced q equals x squared with q greater than or equal to x squared. And because I've written it in this way, you see that this is now a standard inequality that can be imposed using semi-definite programming. Okay? And there's a natural multivariable generalization of this. Basically, you put some vectors here. And q is now a matrix. So in this slightly more general context, we could define a matrix of variables, quadratic variables, q, k, l, where this would be a k, and this would be an l. Right? And x here would just be the collection of, so xi here would just be trace m to the I. So this would be the appropriate generalization of this nonlinear relaxation for the case where we're relaxing more than one variables. And again, there's a generalization of this that you probably can guess for multi-matrices. This is a weaker condition. In principle, we're losing information, but in practice, we end up gaining something because we can go to much higher level than what we could do just by scanning. Yeah. You can check at some fixed level in some, well, in some other problem, in some slightly different context, you can check that at a fixed level, relaxing this constraint sometimes makes the problem worse, and sometimes it keeps it the same. So it depends a little bit. Yeah. Okay, so now performing this nonlinear relaxation on this problem, we can obtain some very high precision estimates of some simple correlators. So one context where it was studied in Kazakov and Zhang, they considered a two-matrix model. So they considered an action that has this commutator squared interaction, and also some potential for x and y. I believe it was a quartic potential in their particular context. So this is some two-matrix model that cannot be solved analytically. Okay? And nevertheless, you can use the Bootstrap, and if you want to compute some simple correlators, you can do so to high precision. So that means like 6 or 7 decimal digits, just with modest computational resources. So this shows that at least you have some model which you cannot solve by hand, which you can now solve using this simple algorithm. Okay, very good. So we've addressed now the first 3 challenges. And finally, we would like to address the sign problem. So the sign problem, for our purposes, we're going to consider the sign problem only in quantum mechanical systems. So we're now going to turn to quantum mechanics as opposed to a 0D matrix integral. Okay. So any questions about the 0D setup, where we're just computing moments of random matrices? Yes.
Okay, complicated technology. In the case of the two-matrix model, for simple potentials, maybe you can integrate out one of the matrix and ended up with a one matrix model that you know how to solve analytically.
Yes.
And then you can check your method, maybe.
Yes.
No?
Yes.
Have
yes.
you tried that?
Thanks. Yeah. So 2 comments. One is like, for example, there's a very simple two-matrix model where we can solve. It falls into the category that you're discussing, where we just have a trace A-B interaction. And then we have, let's say, a trace V of A, trace V of B. And this, indeed, we can solve, and it's related to the minimal string with the Ising model, okay, with the Ising model on the world sheet. And in that context, there's an exact solution, and we checked that it works. Yeah, more generally, of course, this trick that you mentioned works if it's quadratic, let's say, in only one of the A's, right? And then let's say if it's quadratic, you can integrate out. I think this model that Valadia and Zechuan studied does not fall into that category. So there's no trick that I know of, and I think a stronger statement is that there's no trick that Valadia knows of that can be used to solve that model. So at least for now, it seems like it can really solve some, so strongly interacting system.
So in general, if I have to deal with the fermionic matrix model, this doesn't apply?
Yeah, that's a great question. I would really like to know the answer. I don't know how to do.
So as an example, if you take the IKKT matrix,
IKKT, I don't know how to bootstrap IKKT. I suspect that there's some positivity, hidden positivity in IKKT that could be used to do the bootstrap, but I don't have anything super concrete.
I mean, of course, usually for lattice field theory, you have a reflection positivity.
Yes, yes. In IKKT, I think the bulk dual, since there's a S9, it suggests that there's some reflection positivity in the bulk. But how to use that reflection positivity, how to translate that even to the matrix model, I don't know.
Sorry, I missed this point. Can you repeat why IKKT is not positive in this sense?
Yeah, so IKKT has some fermions. If you integrate out the fermions, you get some determinant. That determinant is not positive. It's positive for some very special case, like n equals 2. For some reason, it's positive. But in general n, it's not positive. And yeah. Yeah, I mean, okay, I think that's a point worth discussing. Maybe we can discuss a little bit later. Okay, let's go to quantum mechanics now. So
I'm sorry,
again,
this is a silly confusion, but here you just use hermeticity of the matrix to have this positivity condition.
Yes. Hermeticity of the matrix and positivity of the measure.
Of the measure, okay.
Yes.
There's a class of models that are obtained from a supersymmetric localization of 3D gauge theories, and you could have like a one matrix model, but then the measure is a little more complicated.
You don't have this Vandermonde, you have some more complicated thing. Right?
That's right. Do you know if this method has been applied to that class of?
I personally don't know,
matrix
yeah.
models? Okay.
It would be interesting. Yeah, you have some like trig functions, right, instead of the Vandermonde.
Yeah, you have some cinches, and yeah, that's right. That replaces the Vandermonde. Yeah.
Okay, so in quantum mechanics, we still want two ingredients, positivity and the equations of motion. So, okay, there's a naive approach, which you could say, which is, let's just discretize the quantum mechanics, put it on, let's say, Euclidean time circle, and then think of that as a multi-matrix model, okay? So, of course, you can say that, but it's not going to be a super efficient way of doing this bootstrap. For one thing, you have to discretize, and then we have to worry about, discretization error. And for another thing, you now are in the multi-matrix context, which is more challenging than just the single matrix context, okay? So even if you wanted to solve a one-matrix quantum mechanics using that approach, naively it would be much harder. So there's a simple way out, which is just to use the sort of Hilbert space or Hamiltonian formulation, right? And this was proposed by Hahn, Hartnell, and Krutoff. Okay, so what are the two ingredients in this context? Well, the equations of motion, let's explain that again first. It's now extremely simple. The equations of motion, so the idea is you want to compute, let me state the goal slightly one more time. So let's say the simplest possible goal you could have would be to compute some observable O, let's say in the ground state of this quantum mechanics. That's one goal. Okay. And the ground state is an eigenstate of the Hamiltonian. So the equations of motion that we're going to use are simply this. Okay, this looks kind of trivial, right? This in an energy eigenstate, obviously, this expression is just E expectation O minus O expectation E, which is 0. Okay, so this is a useful equation, though, because if we think in the Hamiltonian formalism, right, this equation generates some relations between simple observables and less simple observables, more complicated observables. We'll see this in action in a second. Okay, so we just enumerate all possible operators, and then we apply the Hamiltonian onto them, and that, using just the commutation relations, we're going to generate more complicated observables. And again, we think of this as some sort of recursion relation, relating higher observables to lower observables. Okay, so let's be more concrete. We could discuss, let's say, the one matrix model. So it's extremely similar to what we wrote down before. Now there's just a p squared, right? So these are now matrices, right? So we have some canonical commutation relations. And these indices are paired, so delta IL and delta JK. So X here is a matrix, right? It's a Hermitian matrix, and its entries now are operators, quantum operators. P, again, is a Hermitian matrix. Its entries are quantum operators, and those quantum operators satisfy the standard, of course, non-relativistic particle commutation relations. Okay? Now, if we're only interested in the ground state, I don't have to tell you more. If I'm interested in other properties, I should discuss whether or not this, this model, which has an additional gauge symmetry, so the SUN symmetry, whether I should treat it as a gauge symmetry or as a global symmetry, right? So we have the option of treating the SUN gauge symmetry, the SUN symmetry as either global symmetry, in which case we sum over all other irreps of SUN, or we treat it as a gauge symmetry where we only project onto the gauge singlet sector. But for the ground state, whether or not we're in the gauge model or ungaged model, it's the same, because the ground state is the gauge singlet of SUN. Okay. So the equations of motion are just this, and also any other symmetries of the problem. So we would have a slight generalization of this where we put some symmetry here. What is the positivity? Now, the positivity is extremely similar to before. The positivity However, now the key idea is instead of using positivity of the measure, we use positivity of the Hilbert space, right? So we use reflection positivity. So again, if we had some polynomial of x, for example, right, we could compute the expectation value, trace p x bar p of x. So this means Hermitian conjugate, right? And this quantity would be positive for any polynomial, right? And that's guaranteed now not by the positivity of the measure, but positivity of the inner product, right? So, yeah, if this is, yeah. Hopefully this is obvious. If it's not obvious, I can explain it slightly more. Okay, so in general, we can make this matrix M. Now, it's also a matrix involving operators, not just the x, but in principle, we could also consider operators formed by x's and p's. So this matrix M is now some huge matrix, and its entries, for example, one particular entry in this matrix could be something like the expectation value of xp, xp, x, or something. Okay, and the idea is we consider single trace operators O. So O is a single trace operator, and the commutation relation between the Hamiltonian and a single trace operator is always single trace. Okay, even at finite n, it's a single trace operator. So this equation will generate relations between single trace operators, a set of linear relations between single trace operators. Okay, so now you should ask me, how did you use large N? Okay, so far I have not used large N in any way up to this point. Okay, so, yeah.
Are both operators on a single time slice, or?
Yes. So we're considering operators that are all evaluated in the Heisenberg picture at 0 time.
Okay.
Yeah.
And
So we're not
that's
devolving.
probably much fewer constraints, right?
Sorry.
You're throwing away a lot of constraints by doing that.
Yeah. So the goal right now is just to compute some single trace operator in the ground state. That's the goal. I think in the third lecture we will hopefully discuss the time-dependent bootstrap, and that will address your question. So yeah, we could ask more generally, compute some time-dependent correlator in these models. Yeah, let's discuss that in the third. Okay, so the only way that large N is actually used is in a very subtle condition, which is just the cyclicity of the trace. So it sounds kind of trivial, but it's a little bit subtle, right? So you have some word like this, right? And cyclicity naively would say you can move the x all the way to here, right? And that would be true, of course, in the matrix integral context. But here, because the matrices have entries that are operators, you generate some additional object when you commute the x through the p, right? So when you push this x to the other side, you have to use the canonical commutation relations, right? And in general, that will create a double trace. So yeah, perhaps I could do an example like this. So when you push this x through this p, the x and p will annihilate basically because of this. So, okay, let's just write an equation. This would be the naive answer where I just move this x through, but there's a correction due to the canonical commutation relations, which generates a double trace. Okay, so you'll get something like this, up to some factors of I. Okay, so this double trace, which arises from cyclicity of the trace, in general, at finite n, we should write it like this. But at infinite n, again, we use large n factorization to write this as now the product of one-point functions. Okay? And that's how we input infinite n. Yeah. So in an interesting paper by Zechuan and Valadia, they also discussed the possibility of inputting finite n by using trace relations. So at finite n, of course, yeah, let me leave it at that for now. So you could also bootstrap this model, let's say, at n equals 3, if you want. So again, we have these quadratic relations. In general, we have to do some non-linear relaxation to deal with this. But the technique is basically the same as what I said in the 0D context. OK, so there's one other ingredient that comes into play for these bootstrapping quantum mechanics. So let's review the situation. So I discussed now how in the quantum mechanical context we can input large n. Again, we can do this at any value of the coupling. We can deal with the sign problem now because we're using positivity of the Hilbert space, which means that even if we have fermions, we don't care, right? The Hilbert space is always, the inner product of the Hilbert space is always positive. So in principle, there's no sign problem. And metastability we can address in a similar way. So we could also study this problem for a potential which is unbounded from below. And again, we would get some similar results. But let me just explain one more ingredient which vastly improves the performance of the Bootstrap, which is to input additional positivity constraint, which is sometimes referred to as ground state positivity. So the idea is we consider this quantity I and j. So this I and j are just labeling possible operators. So this defines some matrix Mij. Okay. Yes. Yeah. Sure. Yeah. So.
I'm surprised that it would be easier to go to finite n in one dimension than it would be in 0 dimensions.
Yeah, in both cases you can go to finite n. So in both cases you can impose the these trace relations, and you can do finite n in that case as well. I think what you might have been referring to is when I was responding to Xi about the double scaling limit. So in the double scaling limit, I'm not quite sure how to approach it. So in principle, of course, you could also approach the double scaling limit by taking n finite and large and then scaling. But directly going to that double scaling limit without either going through infinite n and then doing 1 over n, or taking n finite and then taking the double scaling limit, I'm not sure. Okay, so this additional positivity constraint is again very elementary. So the idea is that this matrix Mij is positive semi-definite. So why? So let's consider the diagonal case, I equals j, right? Then we're just saying that we have some operator. We expand it out in the ground state, right? So we have OHO minus OOH, right? This just says that the energy of, So let's divide both sides by OO. And this thing is supposed to be positive according to this condition, right? And now you see what this positivity means. So this is the energy of the state, which is, so this is the energy in the state psi, where psi is just O times the ground state. So this is an energy that is bigger than the ground state energy, which is just this, E ground state, right? So all we're saying by demanding the positivity of this matrix is that when you perturb the ground state, the energy goes up, which is an obvious statement. Okay. A slight subtlety is in order for the entries of M to be single trace, we need to choose O's and OI's and OJ's, which are themselves adjoint operators, right? So here we can think of this as some OI with IJ indices, and then commutator HOJI, right? This thing produces another adjoint operator, and contracting it with this guy, we get a single trace. Okay, so that's a little bit different than in this equation where we had operators which are single trace. Okay, another sort of, okay. So these are the ingredients that go into the quantum bootstrap, the quantum mechanical bootstrap. And again, we can make some plots. So for example, we can consider the quartic potential, and we can make some plots. So in the quartic potential, we could plot, let's say, trace x squared in the ground state, and another quantity, which we could call just the ground state energy, for example. By the virial theorem, this is also related to the kinetic energy or the potential energy. Okay, so at some low level, we get some shape that is a peninsula, and very quickly we get some island. Okay, so as we go higher and higher levels, we get a very tiny island. So this is actually a very conservative plot. In practice, what happens is the island shrinks by like a factor of 10 very quick as you go up in levels. So you get an extremely tiny island that is the exact value. It converges rapidly to the exact value. So this one matrix model you can also solve, and you get some island. You check that the solution is inside the island. Okay? For the quartic potential. I believe any polynomial potential, this is extremely likely to work. So, but just to be concrete, some potential like this. And you can also study this problem as a function of the coupling. So as I said, if you take G to be negative, eventually the island disappears. And then you rule out the model. So there's some critical value of G in which the island appears to shrink to a point. At some value of G below that, at some finite level, the island actually disappears, and you just rule out the model. Yeah. So again, you can get a very high precision estimate of these simple quantities just by doing this on a laptop. Now, in the remaining time, I think maybe I'll just mention the generalization to the two-matrix quantum mechanics. So you could consider a more complicated model where you have, let's say, trace px squared plus trace py squared plus, let's say, a commutator xy squared. Okay. And then we do not know how to solve, even without any additional potential, we do not know how to solve this model analytically. There's a small generalization. You could put here xi and xj, where these are now vector indices. So there's some OD symmetry under which the x's transform. So more generally, you could write trace pi squared plus commutator xi xj squared, something like this. Okay. And you could try to solve the model. So basically with the ingredients that I already told you about, we did this, and we got some estimates. Again, we got some islands, and they shrank to a very tiny size. Now, maybe I can try to briefly explain. Let's see, I have 5 minutes left, roughly. 20 minutes left. Okay, great. Then I can explain. So maybe just to give you a small taste of these constraints in action, we can just do on the board the constraints for this commutator squared model for some very low level. Okay. So what do I mean by that? So we're going to consider a 2x2 positivity matrix M. So this corresponds to the positivity of two operators, xi and pi. Okay, so the positivity just says, okay, the positivity matrix looks like this. Okay, we can evaluate what trace xi pi is, right? So in particular, we had the commutation relations xp is I, and we also know from time reversal invariance that xp plus px equals 0, basically. So solving these two equations, we learned that trace xp is equal to I over 2. Okay, so this is for one particular matrix. If we have D of the matrices, we get a factor of D over 2 here and a factor of D over 2 here. Okay, so let's think about positivity of this matrix now. So that says that trace x squared is positive, and it also says that the determinant is positive. The determinant is just trace x squared, trace p squared is greater than or equal to 1/4. Right, so here I've defined, so I'm using a shorthand, trace x squared is equal to d, 1 over d times trace xi xi. You could think of x as just one of the particular xi's, right? So this is just the uncertainty principle, right? This is the uncertainty principle that you learned in quantum mechanics. So that's what we learned from positivity of this 2x2 matrix. Now let's turn to the positivity of the ground state matrix. So I'm doing this by hand just to show you how elementary this all is. So the ground state matrix, we call it, well, let me call it N now because there are two kinds of positivity. So M was the inner product matrix. N now is the ground state positivity matrix. Okay? And applying it again to the same operators, we get the following. Okay? So we need to calculate something like H, X, commutator H with X. Commutator of H with X is P, so we get XP. So again, we get these factors of D over 2 here. Let me see if I can get the factors right. Yeah. And then on the off diagonal, we get trace PI. And here we get D minus 1 trace XI. So this is just an elementary exercise of calculating commutators between X's and P's. So you can calculate this 2x2 matrix. Okay, so now let's look at one more constraint, which is the virial theorem. So the virial theorem, that just says, well, first of all, the energy, E in the ground state, can be written as the kinetic plus the potential, right? The virial theorem says that minus 2k plus 4v is equal to 0, right? So in the virial theorem, you get a minus sign whenever there's p's, and you get a plus sign whenever there's x's. And there are 4 x's that enter the potential, so you get a factor of 4. And there's 2 p's in the kinetic potential, the kinetic term, so you get a 2, right? So solving this equation, you get energy is equal to 3/2 k. So we could also write that energy is equal to 3/4 trace pi. Okay? So now let's make a plot. We can plot energy as a function of trace x squared. And we can plot the allowed region. So how do we get the allowed region? Well, again, so this is basically the energy, right? So using this equation, we get 4/3 E. So 4/3 E was just trace pi. We use this equation, we get that this is greater than or equal to d over 4 trace x squared. Okay, I just put the 4's from there. And then we also get another constraint coming from this determinant. So the determinant of n is d over 2 times this thing, right, minus trace p squared, right? So the determinant is this has to be greater than or equal to trace p squared, right? Or we could take the square root of this thing, right? And then using this fact again, we get d minus 1 over 2 trace xi, this quantity to the 1/2, right? So let's plot these two bounds. So the lower bound is just something like this, right? So epsilon is like 1 over x squared. And then the upper bound, there's some square root, right? So we get some peninsula. So the allowed region is some peninsula. So this is the, as you see, we just spent about 2 minutes on the board calculating these first constraints, and we already get some non-trivial lower bound on trace x squared. Okay. Now, you probably know what to do. You just enumerate all possible operators, and you put it on the computer. And you just use semi-definite programming. And so Zetron and I did this, and at high levels, you get a very tiny island. So first comment, since we're all in a Bootstrap meeting, we know every time you see a kink, you should get excited, right? So you might think the exact answer is somewhere close to the kink. And actually, you can look at Monte Carlo studies. So Monte Carlo people have bootstrapped this particular model, and indeed, they have some result that is pretty close to the kink, right? Now you go to higher levels, you get a tiny island, okay? And in fact, we got such a tiny island that we rule out the Monte Carlo result. So their uncertainty was a little bit optimistic, I think. Well, it's not totally trivial because they have to do a large unscaling and continuum extrapolation of their Monte Carlo results. And the systematics of doing that is a little bit subtle. But at any rate, we attain a very tiny island. Now, what can you learn from doing this? So one thing you can learn is that, well, the method works very well, and even with this nonlinear relaxation and so forth, we seem to be able to get an extremely high precision estimate. Okay? Another thing you can do is try to check the so-called large D expansion. So in the conformal bootstrap, we're used to comparing with the ON vector. If there's an ON vector model, we like to compare with large N and try to extrapolate down to finite N, right? And we can do kind of a similar thing here. So this model has an OD symmetry, right? As I mentioned, the X's and P's carry an OD index. And at large D, you can solve this model using OD, and basically the same approximation that you use for the large N vector model, okay? So in particular, in this model, there's a quartic interaction. And you essentially sum bubble diagrams. You can essentially sum bubble diagrams, and this was done partially in some older work. We also worked out some new observables using this method, and we get some OD large D prediction. And so the leading answer is actually not that close to the island, but then if you include the 1 over D correction, so you have to go slightly higher than just tree level sort of in this expansion. So you include the first 1 over D correction, it actually gets very close to the first island that we had. Okay, so that shows that the large D expansion works pretty well. So this is for, yeah, I should say, the large D expansion works pretty well when D is equal to 9. So we did this for 9 bosonic matrices. Yeah, you can also do the same calculation for D equals to 2, and then the large D expansion doesn't work so well. But that's not that surprising. Yeah, so here I've normalized the value of trace x squared to be order 1, let's say. So let's say this value may be 0.3 or something, and we achieve like 10 to the minus 8 in these units. So some observables like trace x squared, we can get them to 6 significant digits or 7 significant digits, depending on the precise model that we're talking about and the level that we went up to. So yeah, we get a very high precision estimate of these results. Yeah, they also rule out the, well, yeah. If you're very strong, you could imagine going to higher orders in 1 over D and trying to see if they really agree with this, how well they could possibly agree. We just went up to the leading order and the first subleading correction.
Is there no?
Yeah, okay, very good. So first we take n goes to infinity, then we take large D. So we first take all the planar diagrams, and then we just throw away all planar diagrams that don't have this bubble diagram structure. It's slightly more subtle because in the usual vector model, there's only one quartic interaction. Here, there's actually 2 types of quartic interactions. So there's trace xi, xj, xi, xj. And there's also trace xi, xi, xj, xj. So there are 2 types of quartic interactions. At leading order, actually, only one of these quartic interactions matters. But at subleading orders, the second, yeah. What I'm trying to say is, from the point of view of this interaction, there's effectively an interaction that's already down by 1 over D. So to go to the subleading order, you need to include 1 loop effects from this guy, and also the 1 over D interaction from the second guy. Yeah.
Is there a large D, useful large D expansion if you have spinner representation?
Not that I, the question is whether there's a useful large D expansion when you have spinners. Well, first comment is, certainly at large D, you can't have more than maybe n equals 2 supersymmetry for these models. Yeah, I need to think about it, yeah. Yeah, I need to think about it. Yeah, you can't directly apply this to BFSS because, well, for one thing, you break the n equals 16 supersymmetries, right, when you go to large D. I don't know if, yeah, even if you just say forget about the supersymmetry, can you do it? I'm not 100% sure. Okay, very good. So let's see. I think I will pretty much end here. Let me make a few more comments. Okay, so one other comment is we can actually estimate the adjoint gap. Okay, so here I'm just talking, so far I've just discussed some simple observables like trace x squared or the ground state energy. Another thing you might ask is, what is the adjoint gap? So in this model, as I said, there's the SUN symmetry, and in the singlet sector, there's some ground state energy, and then there's the first state with the, that transforms in the adjoint, and it has some energy, E adjoint minus E ground state, right? You would like to know what this quantity is. And if you think about it, basically you can obtain it from looking at this matrix, okay? So this matrix says that you perturb the ground state by some adjoint operator, right? So you can perturb the ground state by some adjoint operator and then measure the energy of that thing. So the eigenvalues of n, the smallest eigenvalue of n, should basically be the adjoint energy, okay? And a very simple thing you can do is just take one of these operators to be x. So then you can have h commutator x, and you evaluate this quantity, basically, which we already did here, okay? Here, right? Yeah, so when we evaluate that quantity, it's just d over 2. Now we need to divide by the norm of the state. So the norm of the state is just trace x squared. So basically, very simple bound that you can derive is just delta E is less than 1 over trace xi. I think there's some factors of 2 here. Yeah. Yeah, there's a d over 2 from this d over 2, right? So this estimate actually for d equals 9 is very good. So the Monte Carlo people can also calculate the adjoint gap. They can, so you care about the adjoint gap, let's say if you want to know the Wilson line, right? The Polyakov line in the thermal partition function. So you take the thermal partition function, you insert a Polyakov line, right? And that allows you to extract what the delta E is from Monte Carlo. So we can look at their estimate for delta E, and we actually get very close in d equals 9 by just using the simple bound that delta E is like 1 over trace x squared. And this makes sense because if you think about it, for this to be a precise estimate, all we're basically saying is that x times the vacuum is very close to an energy eigenstate, to the lowest energy eigenstate, okay? And why is that? Well, in the large D limit, the vector-like model is basically a free theory, right? So in the large D limit, x acting on the vacuum just gives an excited state. You can basically think about this as a bunch of harmonic oscillators, right? So x acting on the vacuum gives you the first excited state of a harmonic oscillator. So we get an estimate that's very close to this. Of course, you can try to improve this. So there's some ongoing work by Zechwan and his collaborator where they're trying to more generally try to bound the gap in these contexts. So in other quantum systems, you would also like to know what the gap is for various reasons. And it's kind of interesting that the Bootstrap method, through a very minor modification of the ingredients that we're already talking about, allows you to get access to the gap. Okay, so next time we're going to discuss the application to a model that is more interesting from the point of view of string theory and black holes, which is the BFSS model. So first we will review very quickly the decoupling limit of BFSS and D0 branes. So we're going to just review the gravity dual of that model, and then we'll discuss the applications of these ideas to that model. So in particular, by essentially the same argument that I gave today involving these very small matrices and doing this kind of bootstrap bound, you can get a lower bound on trace x squared, okay? And this lower bound on trace x squared is actually already, let's say, very close. Well, the analytic bound is not that close. Maybe it's a factor of 2 off from the Monte Carlo result, okay? But this is just what you do by hand. Hopefully, when you do numerics, you can get much closer to the true answer for these simple observables. And where we're going is, if you can compute, let's say, these simple quantities, and perhaps you could also compute the thermodynamics in this model, you could test some aspects of the black hole physics. So for example, you could try to test this formula, S is equal to area over 4G, right? Using these simple bootstrap ideas. So I think I will stop for questions.
We have time for questions? You have 3 minutes. Otherwise, we continue during the coffee break.
Yeah, so I think one reason why we might care about it is we could say that we're interested in the Wilson line, in the Polyakov line, right? And in particular, you can think of this as sort of a toy model of confinement. So this is something that people have discussed in the past. So you can think of this as dimensional reduction. Well, okay, let me start. If you take pure Yang-Mills theory, let's say on a torus, and just reduce it, you get this model, right? So the pure Yang-Mills theory on a compact space, when you truncate it to just the zero modes, you get this model. And the phase diagram of this model is very similar to the phase diagram of pure Yang-Mills theory in higher dimensions when it's on a compact space. So in particular, there's a confinement-deconfinement transition, and there's also a Gross-Witten-Wadia transition in these models. So there's two critical temperatures. And one thing that you could ask about is the Polyakov line, right? It has a, one order parameter for these transitions is the Polyakov line. And at low temperatures, close to the ground state, this gap controls the Polyakov line. So I view this as sort of like a first attempt at trying to get some interesting physics of the Polyakov line.
Let's thank Henry for a beautiful lecture. And let's be back at 11:45. here. Oh. Like this is okay, or what is this for? What is this for?
Nothing, yeah.
Very good. So let's get started with Frank on open, closed, open trialities in N equals 4. Okay, first I just want to thank the organizers for inviting me to present my work. In this talk, also matrix models will play the protagonic role as in the previous talk, although without the bootstrap. So the title is this open, closed, open triality that can be realized in N equal 4 super Young Mills. And so let me start by explaining what is this title about. So first, this part of open close just refers to the standard ADCFT, where you start with this stack of n D3 branes in 10D, and you can get a description of open strings that gives you n equal 4 super Young Mills. Or alternatively, you just integrate them out, and you get this closed string description. Now, in order to introduce the third part of this triality that appears when I consider an extra stack of D3 branes, so this I would call little n. This will turn to be what people know as giant gravitons. And this third open description comes from the fact that now that you include this stack of D3 prime branes, a part of the open strings that you would have on the original stack, you will have other type of strings, the ones stretching between the D3 prime branes, and also new strings stretching between the two stacks. And in that sense, there will be now, for some observables, or maybe for all of them, but at least for some we can realize it, there will be a other description for some correlators using the open strings in this extra stack of D3 branes. So this is something that can probably be worked out honestly at the level of this system of the branes, but in this talk I will concentrate on realizing this open-open duality in perturbative super Young Mills. So of course, this description may be more friendly to some strongly coupled super Young Mills. So I will be actually working on the opposite limit of where this description is more friendly. And one outcome or one advantage of using this dual description will be that I will be able to identify some 10-dimensional hidden symmetry of correlation functions. In the planar limit, I'm going to be working in the planar limit. Okay, so let me first continue by introducing what are the operators that play a key role on this duality. So these are going to be what people know as half BPS operators. These are protected operators. The scaling dimension doesn't change at any value of the coupling. And there are when it comes to the description, it really depends on which order of the scaling dimension you consider. So there will be operators of order 1. You can consider VPS operators of order that is equal to the number of colors of the gauge group, or even other operators that are heavy as n squared. In ADS, this would be some gravitons and their KK modes. This would be some branes, such as those D3 pi branes. And this other will be back-reacted geometries, not really pure ADS phi cross phi. First, just let me start with these type of operators, which are the simplest, and they correspond to, in the CFT side, they correspond to single trace operators, which we construct in this way. It's a gauge invariant operator, so we take, it's a composite operator where we take products of the scalar field. We can take k of them. And the trace is taking over the matrix structure of this field, which is NC times NC. This dot just stands for some contraction, where this index I goes from 1 to 6. And it just corresponds to the R-charge polarization of my operator. If you want some interpretation of this Y, it should be associated to the orthogonal directions to the D brane. So they encode on the CFT side the extra dimensions of the S phi of the ADS phi cross phi. For the half VPS condition, there is actually a condition that they are null. So this is what makes this operator to be a symmetric traceless operator, and those are known to be protected. When it comes to compute, let's say, two-point functions, it's a simple exercise because they are just single traces. So if you use this double line notation, you're just instructed to compute this by big contractions. And the trace, in this graph, this vertex has an ordering of the legs due to the trace, and then the only thing you have to take into account is that there is some cyclicity. But the result can be just computed by finding which graphs contribute. And for the two-point function, it's just very simple. It's this graph, and the answer for this case, let's say you are considering here trace of power k, position 1 and 2. The result just take this form, where I introduce these distances. One would be on the R-charge part of the kinematics, and the other is on the space-time part of the kinematics. When it comes to analyze whether they are dual to on the ADS side, this is well identified. So for k equal to 2, this will correspond to the graviton supermultiplet. And the higher k modes, they correspond to kk modes of the graviton due to the reduction to the S phi of the ADS phi cross phi geometry. Something that in the past years people recognize is that studying correlation functions of these operators, if you're studying individually, well, it's still a complicated task because you have to enumerate all of them, and this k can actually take on any value. But now we identify that there is a compact way of describing it, which is to consider the resummation of all of the operators. So we consider an operator which is a generating function that includes the whole tower of CFT operators that are dual to these KK modes. And when we do that, we uncover some hidden symmetry. So let me state what is this 10-dimensional symmetry of correlators, of these VPS correlators. So let me consider this symmetry on the weak coupling side. So I will consider these insertions that I want to compute in super-Young-Mills. And I can compute this as a loop expansion. So G squared to the power L. Here, G squared is the tooth coupling. And here, I will define what we call the loop integrand. So let's say there are n of them. Let's call this x1 up to xn. This way of computing the loop corrections stands for what people call as the Lagrangian insertion method. So it just consists on being able to compute the loop corrections by introducing the Lagrangian of the super-Young-Mills action, and then you are instructed to integrate over those positions of the Lagrangian. So here the integrals only go over the positions of the Lagrangian. This is, well, there are various ways of defining this, but maybe my favorite way in this talk is to do it on the self-dual sector of super-Young-Mills. So you can compute, you can get access to the full correlator, at least perturbatively, by computing these correlation functions in a simpler truncation of the theory, which is this self-dual sector. And, yes. And it is this object, which we call the loop integrand, which satisfies some hidden symmetry. First, let me state that due to supersymmetry, this object is proportional to some factor that we can write in this simple way. These Z and Z bar are the familiar Lycon cross ratios, and alpha bar are just the analog but defined on this R charge with this Y kinematics. And supersymmetry tells you that this correlator is, or this loop correction is proportional to this factor, which is a bunch of zeros that you can go to the zero when you align the space-time and R-charge kinematics. So it basically tells you that there is some special kinematics for some special choices of x and y, where all these loop corrections will vanish. And in particular, you can reach that those zeros on this 2D chiral twist that Leonardo also studies in this theory. So in the 2D chiral twist, this R would be 0. And then you show that in this special case, there are no loop corrections, and then this just becomes some correlator that depends on protected data. But in this talk, I'm not going to do that. I'm going to keep it there and strip out this factor to define what we call attendee symmetry. So let me introduce the operator O as the sum of operators OK, the whole tower, and OK stands for this KK mode operator. To establish the symmetry, let me introduce this notation, which I denote like this. So this just stands for the original 4-point function now with these L insertions of the Lagrangian. This is equal to R times the simpler correlator of the smallest of the operators in this tower, also divided by R. But now here the non-trivial statement is that you can uplift this correlator of the smallest operators, just the stress tensor, to obtain the whole 4-point function that contains all KK modes by making this simple replacement where this 4D distance gets promoted to a 10D distance. which have x and y on the same footing. So in this way, you go from this SO4,2 symmetry of the original 4-point function of small operators to now SO10,2 symmetry, which is the hidden symmetry of this 4-point function. This symmetry holds for the integrand, and in fact, once you perform the integration, it actually messes up the symmetry, so we could say that the symmetry is broken by the integration, so it's more a symmetry that can be identified clearly on this self-dual sector of Young-Mills, of super Young-Mills. However, there is another interesting fact, which is that the same 10D symmetry has been identified in the opposite limit. Let me write it as in the limit where the coupling, the tooth coupling goes to infinity, which in ADS is dual to supergravity 3-level correlators.
Question is, what's the superscript n?
L. This L just stands for the loop order, so just corresponds to the number of Lagrangian insertions here. And the claim is this is for any L, so L bigger or equal than 1. So the statement is that there is a symmetry for all the loop corrections, but at the level of this integrand. And it's the same symmetry that people have identified in this opposite limit of the coupling that is dual to supergravity. Similarly, it has been identified that this symmetry also gets broken when you include alpha prime corrections on the string language. So this could be like 1/g corrections to the correlator. So we have this hidden symmetry that still lacks some type of explanation, although it's a bit intuitive, and we are happy that it exists, given that it sort of realizes the fact that originally you had a theory in 10D that then you, after taking this Maldacena limit, you get this closed string ADS5 cross S5, and then you have to do this KK reduction to S5. But it turns out that if you then try to recover back all the tower of KK modes into a single operator, it appears that this correlator still satisfies some type of 10D symmetry that remembers where it came from. Now, in this talk, I would like to present that using this open-open duality that I described at the beginning, we cannot prove this symmetry, but we can give some evidence that, or we can find a friendly formulation that makes this symmetry more explicit. And not only that, but we can also identify that the symmetry is not only a symmetry of this type of operators, which are single traces, but also appears when we consider more complicated operators, like the operators that are dual to these branes and have this scaling dimension of order n. So let me proceed with that explanation. Yes. So the key will be to consider that we can build some generating function by starting with determinant operators instead of the single traces. So it is just a simple observation that if we consider this determinant 1, 5, x, this is a generating function. In which sense we can see that if you take the limit where y goes to 0, and here by manipulating the y, I really mean that, as I said, it is a null vector. So for instance, it can take this form. It's a 6-dimensional null vector, but there is also a scale that I can control and take it to be small or big while still respecting the null condition. In this limit, there is a simple mathematical identity that what you will obtain is this as a generating function of all these single traces. So this tower that I was describing that satisfies the symmetry is something that you can obtain from this determinant operator when you take this limit. But not only that, this operator contains more interesting type of operators, which you can access if you take, let's say, the limit where y goes to, y is very large. In this case, well, you just get access to this determinant operator, which doesn't really have an expansion in terms of single traces, and it really, if you were to set up the problem of trying to compute the two-point function of this determinant, you will run into some issue because now there is no really cyclic ordering. What defines the determinant is this epsilon tensor, this antisymmetric tensor, which just tells you that any ordering is possible, well, up to a sign. And the naive combinatorics will start telling you that any contraction is possible, even the ones that you would naively rule out by saying that it's non-planar. But here, in fact, they will all contribute, and you will start getting a series that looks a bit thick because it looks like will not converge. But after you do that exercise, you can convince yourself that you can actually resum the series that you obtain, and the result that you get, of course, because of the CFT symmetry, and our symmetry has this form, but it contains also this exponential behavior. So it has this exponential suppression that depends on n. And the physics of this, if you look at it from the point of view of the ADS side, is that this corresponds to some classical object in ADS. That is a heavy object that follows the geodesic. And it is this D3 brane, but not in ADS. In ADS, it's like a point particle. It's a D3 brane that is filling S3, which is inside the S5 part of the geometry on the bulk. So this is the explanation for why the interpretation of this exponential suppressed factor. It should be compared to the action of this classical action of the brane on the ADS side. And for the case of the two-point function, because these correlators are protected, the two-point function is protected, then you can really compare with some holographic computation. Now, this interpretation is still, you can borrow it to try to describe this generating function, given that there are these two limits. What we can say is that we can interpret y as setting the scale of the size, setting the size of the D3 brane inside S3. So just to say that when y is very large, we will be talking about a brane that is filling up this S3. But then when y is small, we think of this shrinking and then going to some limit where it just spits out this set of gravitons. So this determinant is something that can give you access to these both type of correlation functions. One just with an interpretation in terms of graviton particles, and another which is this classical D-brane object in the bulk. These are the operators that are subject to this open-open duality. So let me explain that. This is going, okay. So what I want to present now is what people call matrix duality. Is a statement about the correlation functions of determinant operators. And it can be stated as some result in matrix models. So in this case, we are also including some kinematic dependence on space-time dependence, but that's not the key role, the key point. So we consider these correlation functions of the determinant of these determinant operators. Little n of them in free super Young mills. But here, I mean, I call it free super young mills, but in fact, because these are scalar operators, they just prove the scalar sector. So it would be like a free scalar sector. And which is a Gaussian matrix model of NC times NC matrices. What matrix duality tells us, so let me write here, matrix duality, is that this correlator of these n insertions of these determinant operators in this ensemble of capital N matrices is equal to another partition function. Well, in this case, I'm going to really write as a matrix integral of a row matrix, which is now of order n times n, with some kinetic term, which is also Gaussian. And it also contains some insertion of determinants, but now it's determinants on this new matrix with the power nc. So the way to phrase this equality is to say that there is a partition function that includes this insertion of determinants, little n of them, in this ensemble of capital N times capital N matrices. And on the right-hand side, we have a similar in nature partition function, but where now these two numbers, little n and capital N, get exchanged. Now the matrices on the right-hand side, they have the size of them is controlled by the number of determinants on the left-hand side, and what used to be the size of the matrices now appears just as the number of determinants, which can be considered like a coupling at the level of the action. We claim that this is what stands for open-open duality. And the reason to say that is that, well, we are not going to go through the steps to make this derivation, but it's just a simple derivation that to go from this partition function to this one, which just requires integrating in and out some fields. So we integrate in some fermions and then integrate out the original fields of super young mills to then finally integrate in this matrices row. And these steps can be maybe described also in analogy with this brain construction, where, as we said, there are three types of open strings, and the fermions that I described that you need to integrate in to get rid of the determinants would correspond to these open strings stretching between the D3 and D3 prime branes. And the two descriptions, the left and right-hand side, will just correspond to the fact that if you want to look at the theory on this stack of D branes, you integrate out these fermions, and what you get is some insertion of determinants due to the presence of these D3 prime branes. Or you can do the other way around, look at the theory from this point of view. You integrate out these fermions, and now you get other determinants, but now of matrices that whose size is controlled by the number of D3 prime branes. So this is the reason why we want to establish that matrix duality is equivalent to this. It's a realization of open-open duality, but in this free theory case. Furthermore, I can explain a bit more of how this duality is realized at the level of graphs. So for that, let me consider this limit in the context of this limit where the y's go to 0 and is more friendly to having single traces. If you do that, then all of this just expands into a bunch of single traces, and then you want to do the combinatorics of contracting single traces, which is easier. And let's just describe some type of contribution that will appear in some correlation function. So this is just some part of the graph. Here I'm sending legs somewhere else that contract with other operators. And I'm thinking that here you have at least four traces, and well, there is more here. So these are like our original traces that we obtain on this limit where y goes to 0, and this is a graph that contributes. And the interpretation of what this is in terms of this graph is what people call the graph dual. So we want to make a third statement, well, another statement that matrix duality is open duality, and it's also graph duality. Now these legs or these vertices, they come from expanding this determinant, and the way to read this is that if you consider that this is at position 1, 2, 3, and 4, these matrices will just correspond to the labels will correspond to which traces you have on the neighbors. So this would be like the open string stretching between the brain 1 and 2, so you call it row 1, 2, and so on, row 3, and row 4, 1. So this is, there is no major mystery if you always know that you can dualize a graph, and this is the matrix realization of that operation of graph duality. Now this, just to make sure that it's clear what is the row. So the row matrix is a little n times little n matrix with zeros in the diagonal, because having something here will correspond to a self-contraction, but that is not allowed, so we just have zeros, and then it's just filled in the usual way, and so on. So this little n times little n matrix. This new description is actually more friendly to an analysis of the correlators of determinants. The reason is that now the big parameter n is just a coupling, and the matrices that we have to deal with are just small matrices that are given by the number of determinants on the original description. So this is much more friendly to actually applying some saddle point analysis, and that saddle point analysis will correspond to this, I mean the saddle points of that integral will correspond to these classical objects that we can identify in the bulk. So just let me describe to you how this saddle point analysis goes for the simplest example of a two-point function. So for the two-point function, there will actually only be two non-trivial saddle points. Well, actually one trivial saddle point and one non-trivial saddle point. And that will correspond to, well, what I just erased, which was these two different limits of single traces and this maximal determinant. So we can take this example of n equal 2, the saddle point, just considering that the large parameter here is nc, driving this action over there. And of course, you can write some effective action by bringing this determinant as some type of log of determinant potential. And from there, you can get the trivial case, which will just be, in this case, because we have n equal to 2, it's not really a matrix, but you just have the row 1, 2, and row 2, 1, and they take this value. Or the non-trivial one, which corresponds to these kinematics. They, well, if you evaluate at this saddle point, what you will obtain in the trivial case will be something like this. This would be the leading order plus some 1 over nc corrections. And for the other case, we can show that you obtain this, which must be there for kinematics. But then we can also reproduce this exponential term. And even if you consider fluctuations around that saddle point, we can even get this prefactor. And then, well, there will be other corrections. So these two saddle points correspond to just the case where, well, in this case is what I drew before was the D3 brain filling this S3 inside S5. And here, on the other hand, is more about having a bunch of gravitons that are exchanged. And you have the whole tower of them. And here we see already the appearance of this 10D distance which is the key point on this hidden symmetry. So from the matrix model, we can actually obtain that in this trivial saddle point, there is an effective propagator which already combines the space-time and the R-charge kinematics on the same footing, and that gives you this hint for the 10-dimensional symmetry. Of course, it's going to get more complicated if you consider a higher number of points, so more saddles. And let me just draw it as pictures. So of course, you be the case where you just have the trivial saddle, and then you will just send towers of KK modes. There will be another contribution where you will have a classical brain, and then some tower of KK modes. Another one where maybe now the brain expands into ADS, and there is the tower of this. And then, well, it gets more complicated, of course. And of course, all these saddle points contribute to this correlation function, and they are in competition, and you should consider all of them. And if you play with the kinematics, as we were describing before, you can actually project onto some of them. So by playing with the kinematics of the correlator, you can isolate some saddle points contributing as the biggest contribution for some cases. There is some nice work by Cassia and Gayotto, who study exactly these correlation functions of determinants, exactly this same type of matrix duality, and study these saddle points with the advantage of considering some simpler setup, where you take this 2D chiral twist, which, as I described before, is the one that kills all the loop corrections, and you just get some protected sector. But nevertheless, in terms of the structure due to the large N number of colors, it's still non-trivial, and you still get this structure of saddle points. So they were able to study these saddle point or saddle equations, and even identify a correspondence of those equations with some curves in what they call twisted holography. Of course, we would like to repeat that analysis, but maybe not on this restricted sector, but in the full theory and super young Mills, and understand better these saddle point equations and this competition between saddles. But as you see so far, we only had the free theory description in terms of this matrix integral, and we would like to upgrade this to full super young Mills. However, currently we cannot do that, and but what we achieved with Simon and Beatrix was to improve this duality to include loop corrections in the way of including these Lagrangian insertions that I described before. So what I would like to show now is how we upgrade super young Mills to free super young Mills to perturbative super young Mills, and then study correlation functions on these different saddles. And the output would be that we will be able to identify that there is part of this hidden symmetry that corresponded for the trivial saddle. It will also show up for the other cases, for the other saddles. So it seems to be more general than just the case of single traces. So let me describe to you this upgrade to include loop corrections, and then I will end with presenting the symmetry. So the way that we include the loop corrections is to consider the expansion of super young Mills around its self-dual sector. And that has some advantages that I will now describe. And that's the reason why we consider that, and it will be a friendly formulation for generalizing this matrix duality in a simple way. Although the formulation is not so simple because it requires going to twistor space, but I'm not going to present those details. So you can write the action of super Young Mills as a perturbation around self-dual Young Mills. So SD stands for self-dual Young Mills, super Young Mills. And here you have the tooth coupling with some Lagrangian. And this formulation is due to Chalmers and Siegel. And it has two advantages. The first one is that if you consider this self-dual sector in twistor space, which is a formulation due to Witten, this corresponds to some Chern-Simons theory, which has this cubic interaction. Likewise, I didn't write it here, but self-dual Young Mills itself is not really a free theory, but it contains some interaction vertices. Some of the Yukawa terms of the super Young Mills Lagrangian still survive in this limit. However, the advantage of going to twistor space is that you can consider
Can I ask a question? Can you remind us what are the interesting observables in self-dual Young Mills, like Wilson loops, or what could I compute just in that theory?
So I think, as I said, it's not a free theory, but it's almost like a free theory. So if you consider scattering amplitudes, I think you can just get the tree-level scattering amplitudes, and there are no really loop corrections in the super Young Mills. I mean, you can also consider Wilson loops, but this would just match with the tree-level super Young Mills observables.
So Wilson loops in this theory, they don't get they get only trivial loop corrections?
Yeah, there are no loop corrections. That is really the statement that self-dual Young Mills can be thought as some background around which you can expand. So you can really, if you're interested in tree-level computations for Wilson loops or scattering amplitudes, this is enough. Yeah, and this is the way that actually the amplitude community found many of their simplifications for the scattering amplitudes. And it also, this twistor space formulation of Witten also play a key role in understanding that. The advantage of going to twistor space is that it's a higher dimensional space. It's a 3-complex or 6-dimensional real space, and it has more gauge choices. And in particular, you can make a gauge choice where exactly this interaction vanishes. So then you have a Gaussian theory. Maybe that makes it more explicit to be kind of free. And the second advantage, so Gaussian is something we like because matrix duality is much more friendly when you have a Gaussian model. The second point is that this Lagrangian turns out to be a super partner of the simplest operator O2. So let me write this, introduce these supercharges, acting on this trace of Y-phi square, which is on the stress tensor multiplet. Of course, the bottom component is the operator itself. But then if you go up, and normally this multiplet should go up to order 8. So here, this A is the R charge that goes from 1 to 4, and alpha goes from 1 to 2. So there are 8 of them. And this will go all the way up to theta to the 8. But because of the half VPS condition, it truncates. That's what we call half VPS. So it truncates at theta to the 4. And that top component is exactly this Lagrangian. So that is another advantage, that we can think of the Lagrangian as something that comes from these single traces by just acting with supersymmetry. So the outcome of that is that if we, let me see, we are, given these two facts, we are now invited to upgrade our correlator of determinants to supersymmetrize it first, and then second to go away from this free scalar sector and consider this self-dual Young Mills. So we consider the superdeterminant including this Grassmann superspace kinematics. And this is just this action on the bosonic determinant. Just following this observation from that, well, you can again do the expansion, right? Of course, you get a determinant. And then the claim is that here, because you know that this determinant, this bosonic determinant contains this single trace operator, you will get here on the theta to the 4 component, you will get the Lagrangian, but you will get more than that actually. You will get some operator that also has some y dependence, and this will stand for the Lagrangian plus its KK modes. So what we have here is that well, as I described before, the determinant is a generating function of these scalar operators and all the KK modes, all the KK tower. But when we supersymmetrize it, we also have there the Lagrangian and also the analog of the KK modes of the Lagrangian, the KK modes of these super descendants. So from there, well, there is just this observation that this supercorrelator in self-dual Young-Mills, after you do some y and theta projection, will contain this correlator of the bosonic determinant in particular, and also Lagrangian insertions. And this is exactly what we call loop integrand and what was subject to our 10D symmetry. So what we would like to do is now to apply this matrix duality to this upgrade of super determinants in self-dual Young-Mills. And actually, well, again, I will spare the details, and I'll just tell you that the modification stands just for a simple decoration on this original formula for the scalar case. So let me add this exponential. So it has an index I. This is what I called xi, yi, theta I. And this just modifies this to have some extra interactions that carry all the dependence on the Grassmann part. At the level of the graph, if you look at these single trace vertices, it just corresponds to including here some decorations in between the edges, which come with some labels that you can read off from the position of the operators around it. So here there will be 2, 1, 3, and it will be 3, 2, 4, and so on. What is this delta function? That is something that, well, as I said, it carries all the dependence on the Grassmann. So for pragmatic purposes, this is it. Like the upgrade to self-dual Young-Mills is, the job is all done by this delta function. And in particular, you can now study saddle points of this new matrix integral. It turns out that for some of the simplest saddle points, it will not change, like this delta will not have an effect. Although it could be that actually for more complicated saddle points, now this Grassmann component may introduce some dependence on the saddle point. So that may be a departure of the case study by Cassia and Gayotto. Just let me give you a flavor of what is this delta function. And for that, I need to go back to this twistor space. Yeah, maybe erase here. So I started the talk with this motivation with a stack of D brains on this Maldacena construction of the ADSFT duality. And I made some analogy with those open strings between the D brains and and those fields, and on this matrix integral, right, like there were these open strings stretching between the two stacks, which are absent here because they are exactly those fermions that you integrate out, and in one case you get insertion of determinants in super Young Mills, and in another case you get insertion of these other determinants. And the analogy is good. However, there is another formulation of the branes, which is actually probably the most honest realization of this, closest to this formulation, which is a perturbative formulation of super Young Mills. This corresponds to this twistor string formulation of perturbative super Young Mills due to Witten. So he tells you that if you want to obtain super Young Mills, but not the full thing, but just perturbative, you start with a stack of NC D5 branes, filling up the whole space of CP3/4, which is the twistor space. And if you just consider this theory, well, it's actually a topological string theory, and what you obtain from here is what people call holomorphic Chern-Simons, and that, if you go back to from twistor space back to the standard R4 space, that is just self-dual Young Mills. So that is this topological string realization of just the self-dual sector of super Young Mills. So, but in order to complement the full description of super Young Mills, he also figured out that you need to include an extra set of branes, which are the one branes, wrapping a line in twistor space. A line in twistor space is a CP1 line. And that sources other type of open strings, whose interactions will complement the self-dual sector of Young Mills to the full theory. In fact, in this formulation, what is interesting is that having all this open string, what you obtain is actually an infinite tower of vertices. So it's a less familiar realization, as opposed to the Lagrangian that you write in 4D, which is just a finite number of terms. When you go to twistor space, you can find that there is a realization of that Lagrangian, but now with an infinite number of vertices. And this is very familiar to the amplitude community because those vertices correspond to what people call MHB vertices, and allows you to come up with different ways of factorizing scattering amplitudes in super Young Mills, or computing them. In our case, what we managed to do with Simon and Beatrix was to consider the same setup, except for, so here, let's say you have these fields at some coordinates. We just include some supersymmetry. So we also gave some fermionic coordinate. And the statement is that it is this interaction of these fields which stands for this propagator here. So if you go to this twistor realization, these strings that extend between D5 and D1 branes, those are the ones that account for this decoration of delta. And then when we integrate them out, they still appear dressing the determinant in this way that I described on the graph. This is about all I want to say about the twistor part. And now let me just finish by telling you that with this machinery, and given that, as I described, the saddle point, at least for the first simplest saddles, is not much affected by this decoration, we can go to that saddle and then consider some probes, like this infinite tower of KK modes, and compute what is the correlation function of between these determinants, these the branes on the bulk, and these towers of KK modes. So that is something that You can compute starting from this superdeterminant operator. And we actually also consider, sorry. So let me consider two of them that will be more isolated. They are the ones that are going to give me the saddle point. And just to turn the rest into something that doesn't affect the saddle point, we dress them with some extra exponents that then we just take to 0. This is known as the replica limit. And then we also take the y's to infinity, such that we go to this saddle point of the maximal giant graviton. In this case, what you will obtain will be this determinant of y phi. Let's call that d. 1, 2 of them. And then the rest will be a bunch of log of determinants. That is something that you actually extract by taking this limit. And the log of determinant is the sum over all traces. So we are really talking about this tower. And then some Lagrangian insertions, which would be the ones that give you the loop corrections. And the statement is that now for this new correlator, we can also state a symmetry. So well, let me just repeat that. This is this, and this is this, which is the tower of KK modes. This is KK tower. And we can, let's define this. L is the number of loop insertions. And there is a symmetry. Again, this R factor, which is the one that vanishes on this 2D chiral twist, is something that is determined by supersymmetry, and it doesn't really matter which type of operators, I mean, in terms of matrices or traces of determinants, this will always be present there. And the statement is that we normalize by the 2-point function. There is again a 10D symmetry. But now there is a modification for the case where you have an interaction with the points 1 and 2, which stand for the maximal giants that give you this this geodesic in ADS. So this is the statement of now 10D symmetry, but now in a non-trivial saddle point. And what is interesting is that while this is the weak coupling setup, actually, again, thanks to some work by recent work by Shinan and Junfen, in supergravity, by considering this case where you have this geodesic given by these heavy objects and this tower of KK modes, they find same 10D symmetry. And okay, of course, then we would like to conjecture that this will hold for all saddle points, and of course, we are trying to explore that. Although, well, this is, as I said, still work in progress, and but yeah, we can. I think from this open duality, it appears that we have the power to identify that this type of poles of that combine space-time and R symmetry is something that is a feature of all saddle points of all the correlation function of these determinant operators. So let me just finish by mentioning a couple of points that I didn't address and could be interesting. And this, well, of course, one point is to understand this standard symmetry, right? Like, it's something that is very peculiar. It appears in the weak coupling formulation. Strictly speaking, this would be a symmetry of the self-dual sector of Young-Mills, and we can phrase as the loop integrands of the full super Young-Mills. But then it also appears on this three-level supergravity. So it would be nice to, from the language of the string theory, is about this infinite tension and this tensionless limit. So it would be nice to maybe have some string theory explanation of this observation. And well, as I said, just let me say that, then the symmetry Y. And then the other point is that we can also consider maybe these NC square order operators. This would be like determinants to the power NC. And they would be these back-reacted geometries. And maybe we can have these probes. The matrix duality is a true identity for every value of n and every number of determinants. So there is nothing that stops us from considering this, except that now then you lose some advantage, because one advantage before was that now the new matrix was a small matrix, but now the matrix will have the order of this exponent, which will be just the original size of the matrix in super Young-Mills. And then you will also have these determinants to the power NC. So, but of course, maybe if one can consider this large n approximation, there could be a way to address these operators. And since we know how to compute the loop corrections, it would be nice to see if there is also some sign of hidden symmetry for these more complicated cases that correspond to back-reacted geometries. And something maybe more simple is to consider NC finite and large charge. This would correspond to consider a determinant that maybe would be for NC equal to 2. So just a simple determinant to the power j. And in this case, the matrix model will be of order j times j, which is taken to infinity, so it's a large matrix. But now the determinant is just some small power. And one outcome of this open-open duality would be that now you will be able to phrase this limit as some type of tooth limit, but it will be a tooth limit in this dual open formulation. So it is secretly a tooth limit, but you have to go to the other set of D-branes. Okay, so that's all I wanted to describe today. Thank you.
Questions for Frank?
So in this last thing you were talking about, if you do large n and large charge, they'd be dual to some LLM geometries in the bulk. So can you look at strong coupling in the bulk directly and then see if there's hints of this open-open duality? So you have some annulus region for the LLM, and then you can maybe change the radius of this annulus. And
right, okay, that would be interesting to address, but yeah, we haven't reached yet this level of considering both parameters large. But yeah, I mean, if you can, as I described, this open-open duality is something that maybe you can also study at the level of the original D-brane construction holographically. So maybe by studying these open strings directly in ADS, you can realize this duality. But yeah, for the free theory, for the perturbative case, you have to wait.
More question? If not, let's thank Frank and go for lunch. And let me remind people that right now we have the strings conference going on at the same time. So some of you are here because of that. And today in the afternoon we have a talk